Standard cast-in-place concrete relies on gravity, dropping a fluid mass vertically into a form. Shotcrete relies on high-velocity impact, driving a horizontal stream of material directly against a receiving surface. The inspection process begins with standard verifications. The inspector checks bar size, grade, spacing, location, and embedments against the project documents. But perfect adherence to the structural drawings does not guarantee success. A reinforcement layout can match the plans down to the millimeter and still cause severe placement difficulties. For shotcrete, reinforcement must be shootable. The material stream requires physical access to reach entirely behind and tightly wrap around every single bar. A two-dimensional layout on paper offers no value if the physical, three-dimensional arrangement blocks the material from encapsulating the steel in the field. Encapsulating that steel requires the cage to absorb immense kinetic energy. When a high-velocity stream of wet concrete strikes a surface, the impact is violent. If the reinforcement cage is loosely tied or only standardly secured, that kinetic force causes the steel to shudder and shift upon impact. The moment those bars move under pressure, the carefully measured spacing, alignment, and cover metrics are immediately compromised. A cage that appears compliant during a quiet pre-placement walkthrough will fail during shooting if it lacks absolute rigidity. A static visual inspection is inadequate. The inspector must evaluate the reinforcement's capacity to withstand a dynamic impact without shifting. Rigidity is only the first requirement. The steel must also be clean. All reinforcement has to be entirely free of materials that inhibit the bond before placement begins. Hardened overspray on the face of the reinforcement is a critical defect. Once dry, it actively blocks new shotcrete from bonding directly to the bar. You cannot evaluate this cleanliness by standing directly in front of the wall. The inspection requires walking completely around the cage, checking corners, forms, and the hidden backsides of the steel where overspray accumulates. Evaluating cleanliness solely from a front elevation guarantees that hidden defects will remain undiscovered, permanently compromising the structural bond. The nozzle stream obeys fluid dynamics. To build a solid structure, the material requires a clear, unobstructed path past the front plane of the steel. When bars are spaced too closely, material builds up and connects across their front faces. This bridge starves the rear space, creating a critical empty void, known as a shadow, directly behind the reinforcement. Clearance is the geometric prerequisite for material to consolidate from the back surface forward. Measuring it solely to ensure aggregate fits ignores the path necessary for full encapsulation. Evaluating rebar spacing on a flat, two-dimensional plan view offers a deceptive simplicity. The physical reality of the field is more complex. Congestion multiplies through overlapping elements. The layout often includes multiple bar layers, bulky mechanical couplers, heavy anchors, embedded plates, and intersecting water stops. These overlapping obstacles dictate where the nozzleman can stand, restrict available shooting angles, and trap escaping rebound within the cage. Congestion is a volumetric blockage problem. It must be evaluated by how the combined obstacles restrict access, rather than simply measuring the distance between two front-facing bars. This spatial interference is especially severe at reinforcement lap splices. ACI 506.2 limits the required separation for these splices based on bar diameter and maximum aggregate size. Non-contact laps are the preferred standard. This separation allows high-velocity material to flow completely between bars. But contact laps present a challenge. Touching bars act as a continuous screen, creating a significantly larger blind spot that blocks the shooting direction. Memorizing spacing codes is a starting point, but the inspector must verify that the actual physical arrangement on site allows for complete encapsulation. Consider a field scenario where an inspector reviews a rebar cage and confirms that every bar is the correct size, properly located, and structurally compliant. However, a massive scaffold tube is positioned directly in front of the placement zone. Even though the steel is correct, this external obstruction prevents the nozzleman from maintaining a workable angle, rendering the cage unshootable. An inspector must always evaluate the entire physical placement environment. These external spatial constraints will inevitably dictate internal structural success. Now, imagine extreme congestion at a construction joint laden with multiple steel layers and couplers. The contractor insists the layout matches the drawings exactly. In the field, the inspector's authority has limits. You aren't there to redesign the reinforcement layout. Your responsibility is to identify the placement difficulty, ensure pre-construction procedures are followed, and observe the area with extra care during shooting. Once shooting begins, active observation is critical. The most severe warning sign is observing dark, empty pockets behind front faces already coated in gray shotcrete. You must halt placement process and correct the nozzle technique before that hidden void is permanently buried. The inspector's role evolves from checking static compliance before the pour to active forensic defect detection while the material is flying. This creates a fundamental operational split. Pre-placement inspection evaluates the steel. Active placement inspection evaluates the encapsulation. These phases follow a four-question loop. First, what should I see? The answer is correct, clean, secure steel with sufficient access. Second, what am I seeing? Here, you identify deviations like contaminated steel or blocked angles. Third, why does it matter? Because these create void risks. Finally, what action is required? Confirming correct reinforcement can never replace verifying complete encapsulation. They are two halves of the same job. Effective inspection requires three things. Reinforcement must be shootable, congestion viewed in 3 dimensions, and you must verify both steel and encapsulation. Regardless of the drawings, the ultimate field question always remains. Can the shotcrete actually get completely behind the bars? Validating the steel is just the beginning. Next, we focus on the forms, embedments, and the site's overall access.